Hi, Physics, Mr. Janowski. This is Chapter 13, Homework 4, Problem 5. And there's lots of parts to this one. There's another page, another Jamboard for this. So either I'll make one video or two. We'll see. So what's going on? A 1 kilogram object falls from rest out of the Kuiper belt towards the sun. The Kuiper belt is way out beyond, all of the planets. It's a belt of objects way out in the distant solar system. So grab the red pen. Step, Part A. What is the GPE of the object when it leaves the Kuiper belt, which is essentially infinitely far away? Okay, so we're looking for GPE. GPE will be something in joules. Okay, so for part A, our new formula for GPE. The Chapter 9 version is for like when you're lifting things up from near the surface of the Earth and letting them go. This is the one, the equation you have to use when things are starting at like astronomical distances, when things are in orbit and things like that. So our formula is this. So GPE is equal to minus big G, mass 1, mass 2 over R. Okay. Well, this thing is starting essentially infinitely far away. So what that means is, I could put in the numbers for big G, for M1, 1 kilogram, for M2, the mass of the sun, but the distance it is away is infinity meters. So any finite number divided by infinity is going to give you 0. Convince yourself of that. If you take some number that isn't infinite and divide it by infinity, you get 0. So our answer for part A is just 0. Now for part B. So what is the object's GPE when it reaches the surface of the sun? Okay, so we're again looking for GPE is equal to question mark joules. Same exact formula. Again, I'm a big fan of start with the formula. Like literally write the formula you're going to use. All of this over R. Okay. This time R is not going to be infinity. We actually have to put in the numbers and do the math here. So what do we have? Minus big G, 6.67 times 10 to the minus 11th. M1 is the mass of the thing, 1 kilogram. M2 is the other mass. The other mass is the sun. The sun has this mass, 1.99 times 10 to the 30th kilograms. All of this divided by R. Okay, well, what's R? Well, let's think about what's happening here. The object starts at rest way out in, I'll change color so it's clear what's going on here. This thing starts way out at rest, out in the Kuiper belt. It's going to fall towards the sun. So there's the sun, a sloppily drawn sun. So this first distance, this is the one that I called infinity. Too sloppy. Slightly better, but I'm happy. So that distance was infinity. It's at rest, no speed lines. It was infinity meters away. So that's how we got our answer for part A. So for part B, this thing falls. It's going to take a very long time, but eventually it's going to get to the surface of the sun. So here it is, crashing into the sun, meaning there are speed lines behind it. It's going to be moving. How far away is it? Well, it's 1 radius of the sun. So that's the distance I just indicated there. It's 1 radius of the sun away, which means the R in this one, well, that's going to be the radius of the sun. 6.96 times 10 to the 8th meters. So when I do this in the calculator, don't forget the minus at the beginning. That's important. Minus 6.67 EE minus 11 times 1.00 times 1.99 EE 30 divided by 6.96 EE 8. If you do all that, you get minus 1.907. I'll keep an extra digit here. 1.90708. Okay, so I'll leave it there. Times 10 to the 11th. And what are the units of this? Well, it's GPE, it's energy. So it's joules. So that's our GPE. So, yeah, there you go. And that's, that matches the answer we got there. On to C. Okay. Again, physics will make you one with everything. So we're going to do the same exact thing we used in Chapter 9 for like dropping springs on masses and, Alice going down the slide, things like that. We're going to use the exact same idea that worked for those things to figure out how this thing is moving when it crashes into the sun. Because, again, physics, it's one law that rules everything in the universe, or one set of laws. So, using the conservation of energy, any results from parts A and B, what is the object's kinetic energy when it reaches the surface of the sun? Assume it doesn't burn up before then. And there's other things going on, solar wind and different things like that, but don't worry about that. So yeah, you could do this with the whole strategy with the step 1, make your 2 sketches. I'll do it that way. Scratch that. I'm going to do step first. What is the object's kinetic energy? Okay. So KE is equal to question mark joules. Then if we were going to do the strategy, we would make 2 sketches, initial and final. I've got it all here in one, but let's call this. So this is our sketch. Step 2 would be to write the law of conservation of energy. So sigma E initial plus sigma work external is equal to sigma E final. That idea right there. Okay, well, initially, what kinds of energy does it have? Was it moving initially? No, it wasn't moving initially, so there was no kinetic energy initially. Was there GPE? Again, you can't do the height above 0 thing. You could say, is it at a distance that's not infinite? Maybe that works. But the point is, GPE initial, there was none initially. That was our answer for part A. There's no springs. There's no springs this big. We're not worried about that. And there's no work external. That's just going to be 0. So what that means is the whole left side is going to end up being 0. This is equal to sigma E final. All right, so look what's happening over here at the end of this situation. Is it moving? Yes, it's moving. It's, in the process of crashing into the sun, so it's definitely moving, which means we do have KE final. Is there GPE final? Yes, there was. Our answer for part B was not negative. I'm sorry, it was not 0. It was negative. It was not 0. So that means there is GPE final. So really what we've got is, I'll take it over here, write it a little bit bigger. 0 is equal to KE final plus GPE final. Okay. We're trying to solve for KE. So what that means is, subtract GPE from both sides. So minus GPE final is equal to KE final. So minus, and remember GPE final is minus 1.907 times 10 to the 11th joules is equal to KE final. Therefore, KE final ends up being positive 1.907 times 10 to the 11th joules. So there's your answer. GPE can be negative, or 0. KE, if the thing is moving, KE has to be positive. Right. It can be 0 or it can be positive. KE can never be negative. All right, so let's keep going. I'll make one big video for this instead. We'll go to the next one. I'll just remember that number, 1.907 times 10 to the 11th joules. So let me jot that down. KE final is 1.907 times 10 to the 11th joules. Yeah. All right, so for D, I'll save a little bit of space here. Step part D. What is the object's velocity at this point? Okay, so what we want is V final is equal to question mark meters per second. Okay, How can we get that? Well, we've got a formula for KE. Did I give you the formula for KE down here? No, I didn't. But you remember it anyway. So for part D, KE is equal to 1 half mv squared. Okay, that means V is going to end up being the square root of 2 KE over m. Multiply both sides by 2, divide both sides by m, take the square root. You end up with this. Okay, so the square root of 2 times KE, that was our answer for the last part, 1.907 times 10 to the 11th joules. Boop. Divided by m. M is not the mass of the sun. M is the mass of the object. And remember, our object had a 1 kilogram mass. So all this divided by 1. All right, so in the calculator, 2 times 1.907 EE11 divided by 1. And I've got 3.814 EE11, but I need the square root of this number. So I'm going to use the X to the box button, take it to the 1/2 power. And when I do that, my calculator tells me 617,575.9. This is in meters per second. Okay. Let's put the commas in. 1, 2, 3. So there's a comma. So yeah, you could leave the number like this. That's not a crazy, ridiculous number to write. But if you wanted to do it in scientific notation, this would be, we're moving the decimal over 1, 2, 3, 4, 5 to get it to here. So this ends up being 6.17. I'll keep one more. 7 to 5 rounds up to 6 times 10 to the 5th meters per second. Okay. So there's my velocity there. Okay. So what's going on for part E? What was the object's velocity when it was a distance equal to the radius of Earth's orbit from the sun? Okay, so step for part E. Another one where we're looking for V final, but V final in like a different, a different scenario here. Yeah, so again, let me go back to the other one. I won't redo the whole sketch. What was the object's velocity when it was a distance equal to the radius of the Earth's orbit from the sun? So here was our sketch. We started out at the Kuiper belt. We're going to end up crashing into the sun. This one is saying, not at that point, but when you were 1 Earth orbit radius away. So when the object is something like here, if that distance there is radius of Earth's orbit, how fast is it moving at this point? Okay, so how can we do that? Same idea, law of conservation of energy. So sigma E initial plus sigma work external is equal to sigma E final. There's not going to be any external work, so that'll be 0. Okay, initially, when this thing was out in the Kuiper belt and it was infinitely far away and it wasn't moving, it had no kinetic energy and it had no GPE. So the left side is still 0, plus that is going to equal sigma E final. Okay, so at the end, it's moving, so there is a KE final, and it would have GPE because it's no longer infinitely far away from the sun. So there would also be GPE final. So 0 is equal to KE final plus GPE final. All right, so 0 is equal to KE final is going to be 1/2 m V final squared plus GPE final is going to be plus, remember your formula for GPE has this negative there, so plus negative G M1 M2 over R. Okay, well, I'm going to get rid of this guy because it's annoying me. So plus negative is just become minus. All right, so this little bit of math that I have here, I've got to solve it for V. So first, add this thing to both sides. We're going to end up with, on the left, G M1 M2 over R. This is equal to 1/2 M V final squared. Okay. I've got to solve this for V, so I'm going to multiply both sides by 2. I'm going to divide both sides by M, and then I'm going to take the square root of that. So, and I'm just, for fun, I'm going to flip left and right too. So I'm going to end up with this. V final is equal to big square root 2 G M1 M2 over R times M. Okay, well, which M is this? This is the mass of the object. This is really M1. Okay, which is 1 kilogram. I could put it in there, but notice also that they just cancel. Those guys are going away. I wish I had introduced the square root a little bit later there, but okay. Either way, it's fine. Yeah, so I've got to do this in the calculator. I guess I could have canceled the m's right there as well. Okay, so what do we have? Big square root 2 times 6.67 times 10 to the minus 11th times m2, that's the mass of the sun, this number, 1.99 times 10 to the 30th kilograms, divided by r. Okay, so remember, we're doing this when this thing is a distance equal to the radius of the Earth's orbit. So the r we're going to use is this number, radius of the Earth's orbit. So 1.50 times 10 to the 11th meters. All right, so if I can get this in the calculator, that'll give me my number for V final. So 2 times 6.67 EE minus 11 times 1.99 EE 30 divided by 1.50 EE 11. Now I hit enter. And this gives me the thing under the square root. So now I have to take the square root. I have 1.769773333. So I'm not going to write that down. I'm just going to hit the X to the box button and raise it to the 1/2 power. And I end up with 42068 and change meters per second. Okay, so let me put the comma back in. So 42,068 meters per second. Okay. So that's fast, 42,000 meters per second is 84,000 miles per hour. It's fast, but notice it's not as fast as the other number, the one we just got for part D. Well, that makes sense because as this thing is falling into the sun, it'll be moving pretty quickly when it passes the Earth, but it's going to be moving faster still once it gets to the sun. So that's what's going on there. And finally, part F. I mean, this video is getting long, but we're covering a lot of ground here, so that's cool. How far from the sun was it when it was moving at half its maximum speed, meaning the speed at which it crashed into the sun, which was our answer for part D? So what we're solving for here is R. R is equal to question mark meters. Okay, so how are we going to get to this? I could do the whole thing over again, but instead, let's start with this idea right here. It would end up being the same situation. You could start the law of conservation of energy, do all the stuff. You end up with this. You get down to this expression right here. So the expression was GM1 M2 over R is equal to 1/2 M. Well, this is really M1 V final squared. Well, just V squared. Okay. And at this point, I can cancel the m's. So the m's go away. I will write it again to be clear. Okay. GM2 over R is equal to 1/2 V squared. I've just got to solve this for R. R is the thing we're looking for. So I will multiply both sides by R, multiply both sides by 2, divide both sides by v squared. If I do all that, I'm going to change colors again. Sorry, cramped for space here. If I do all of this and solve it for r, and I'm going to, I'll keep it the other way. So on the left, I would have 2gm2 over v squared. This is equal to r. So again, multiply both sides by r, multiplied both sides by 2, divided both sides by v squared. So I did a bunch of algebra there at once. I get down to here. Now I will switch it. So r ends up being equal to 2 times g, 6.67 times 10 to the minus 11th, times m2, the mass of the sun, 1.99 times 10 to the 30th kilograms. Okay, over v squared. Well, how fast is it moving? Remember, the whole bit was half its maximum speed. So I just need half of this number. It's up to you how you want to do this. You could do it separately. Might make the most sense, but I'm going to do it my way instead. To get half of that number, I'm just going to do 1/2. How am I going to do this? 1/2 times 6.176 times 10 to the 5th meters per second. Okay, so that's my v. Remember, it's got to be v squared. So I got to put big parentheses around the whole thing and square the whole thing, including the half part has to get squared. So a fairly tedious thing to put in your calculator, but let's see if I can get this right. 2 times 6.67 EE minus 11 times 1.99 EE 30. All right, now I'm going to hit enter. 2.65466 EE 20. All right, I want to divide by parentheses 0.5 times 6.176 EE 5, close the parentheses, and hit x squared. If I do all of that, I end up with r is equal to 278,390,4434 meters. Okay, that's a little unwieldy. Let me go back in and put the commas in. So 1, 2, 3 gives me a comma. 1, 2, 3 gives me a comma. 1, 2, 3 gives me a comma. All right, so to put this in scientific notation, how many places have I moved my decimal point? I'll change colors, might make it clear, clear to see. So we started here. 1, 2, 3 gets you to a comma. 4, 5, 6 is another comma. 7, 8, 9. So I'm moving it over 9 places. So this big unwieldy number is the same thing as r is equal to 2.78 times 10 to the 9th meters. 2.78 billion meters. Yeah, that number is big. I'd rather write that as in scientific notation. So there you go. Fairly tricky problem. Hopefully this explanation made sense. And hopefully this video was not too long so as to be completely unwatchable. But anyhow, I hope that helped.